The plasma cutter. It uses a bolt of electricity to transform air into plasma for the ultimate fine cut. The laptop cooling system. Amazing little pipes that are working hard to take the heat and get rid of it with the help of a little water. The chain hoist. All it needs is 2 chains and a set of gears to concentrate one man's pulling power into superhuman lifting power. And the flexible rotary power tool. To transmit movement through a flexible cable, it has to be rigid and yet flexible at the same time. Its secret weapon? A helix. How does it work? We take things apart so you don't have to. The plasma cutter. It's used to cut metal with extreme precision. What bursts from the torch is nearly twice as fast as the speed of sound, and nearly twice as hot as the surface of the sun. But what's most fascinating is that to make this happen, all the cutter uses is electricity and compressed air, nothing else. But by making them interact, the cutter transforms the air. Emerging from the torch, air is no longer a gas, it's a plasma, a state of matter so full of energy it can make metal vanish into vapor. So how does it work? The plasma cutter, the power cord, the compressed air hose, the tube which sends electricity and compressed air to the torch itself, and a clamp, the positive terminal. When the plasma cutter is turned on, the alternating current goes through the case, where a transformer and a rectifier station change its voltage and turn it into direct current. Then it reaches the torch. The compressed air is also sent through the same tube to the torch. Their contact transforms the air from its gas state into plasma, which is incredibly hot. The plasma bursts out fast, over 2,000 kilometers per hour, and it's hot, 10,000 degrees Celsius. It melts metal instantly, and some of that metal is even vaporized. The result? A cut that is incredibly clean and precise. But to understand how the plasma cutter transforms air from gas into plasma to cut metal, we have to take it apart. At the center of the torch, in a small canal, is a negative electrode. The sides of the canal are positive. This difference in polarity is essential to the creation of plasma. When the plasma cutter is at work, the electricity and compressed air reach the torch through the same tube, but they never actually make contact. The compressed air fills the space around the canal, and inside, it fills in around the electrode. As for the electric current, it reaches the negative electrode and, attracted by the positive surface of the sides, jumps from one to the other, creating a small electric arc. The compressed air in contact with this miniature lightning bolt is intensely excited and undergoes a violent change of state. The air is no longer a gas. It becomes a hyper-energized mix of positive ions and free electrons. It's now a plasma. But the plasma is still confined to the torch, and to cut metal, it must get out. That's where the positive terminal clamped onto the metal comes into play, to make the whole surface positive. When the torch is moved close to the metal, That metal offers a much larger positive surface than the sides of the canal. The positive terminal attracts all the electric current. There's no risk of electrocution, not even for anyone who touches the metal surface. The electric arc jumps from the sides of the canal to the metal surface. The plasma instantly bursts out of the torch. It's so hot that it melts and even vaporizes the metal. The molten or vaporized metal is immediately pushed away by the jets of air that come from around the canal. The result, one clean and precise cut, using only air and electricity. The plasma cutter. Using a bolt of electricity, it transforms compressed air into plasma. A state of matter so highly energized that it can cut metal instantly and easily. A bright and spectacular piece of kit. Next, on how does it work? The laptop cooling system. Amazing little pipes that are working hard to take the heat and get rid of it. The laptop computer cooling system. It's often overlooked, and yet it's an essential system. Without it, the amount of heat generated during the computer use could destroy the computer. It's a system that must be both extremely compact and extremely efficient. Everything about it depends on heat pipes, components that take advantage of two things: conduction and changes in the state of water. All this in order to capture heat on the inside and expel it on the outside. But how does it work? The laptop, the motherboard, with microprocessors that generate incredible amounts of heat. A fan, some cooling fins, and connecting the fins to the main heat sources, those heat pipes. They're special copper pathways, both hollow and airtight. Nothing goes in and nothing comes out. When the laptop is working, its components heat up, some reaching over 100 degrees Celsius. Luckily, even though they're airtight, the heat pipes are able to capture heat at one end and transfer it all the way to the other end. Essentially, they get rid of the heat by transferring it to the fins. The fan circulates air, which absorbs all this heat, and then it's blown outside. But to understand how airtight pipes can capture, transport, and get rid of heat, let's take it apart. The heat pipes are in contact with the laptop components that generate all the heat. They're right below them, and even though the pipes are hollow, they're not empty. Copper filaments line the pipe's cavity, and in between them is pure water in liquid form. Now, when two objects physically touch each other, heat is spontaneously transferred from hot to cold. That's conduction. So when the laptop's components heat up, the surface of the heat pipe absorbs the heat through conduction. Inside the cavity of the heat pipe, the temperature climbs, and the liquid water between the filaments starts to absorb the heat. It evaporates. It changes state. This hot water vapor fills the cavity of the heat pipe surrounding the filaments. And so begins a cycle that lets the heat pipe transfer the heat outside. At the other end, the sides of the heat pipe are cool, because they're in contact with the fins, which are being constantly cooled by circulating air. The sides of the pipe absorb the heat of the water vapor. As it loses its heat, the water changes state again. It reverts to its liquid form and begins to collect between the copper filaments. Gradually, it fills the spaces between the filaments until it reaches the hot end of the heat pipe, where it evaporates once again. In the copper filaments, the heat-laden water that evaporates is constantly replaced by cool water, so the cycle continues. The heat transferred from the microprocessors to the pipes at one end and from the pipes to the cooling fins at the other is all thanks to the beauty of conduction. And the movement of the heat between the two ends of the pipe is only made possible by the changing states of water inside the heat pipes. That's how the heat is captured, moved, and expelled. The laptop computer cooling system. It's small-scale, ingenious, and efficient. Thanks to heat pipes, which have mastered conduction and changes in the state of water, laptop computers can be overworked without overheating. Coming up on How Does It Work? The chain hoist. All it needs is 2 chains and a set of gears to concentrate one man's pulling power into superhuman lifting power. And the flexible rotary power tool. It has to be rigid and flexible at the same time by using its secret weapon. The chain hoist. It helps lift heavy loads. It's got 2 lengths of chain, one that's pulled by hand and the other that lifts the load. The force exerted by pulling the hand chain down 30 chain links gets multiplied into lifting the load with 30 times more force, as it takes the load 1 link higher. That's what the chain hoist does. It concentrates the force by transforming a small effort exerted over a long distance into a huge force exerted over a short distance. But how does it work? The chain hoist. The hand chain, cog, drive shaft, gears, load chain sprocket, load chain. The entire hoist unit gets hooked above the weight to be lifted. The load chain is attached to the weight. When the hand chain is pulled, it turns the cog. The cog then turns the drive shaft, which turns the gears, which turns the load chain sprocket, which lifts the load chain and the load with 30 times more force than was pulled. To find out how those gears concentrate the force and do some heavy lifting, we've got to take it apart. The hand chain links fit into 7 specially designed slots in the cog. As the hand chain is pulled, it turns the cog. The cog first screws tight to the friction plate, which is attached to a ratchet wheel. So as the cog, plate and wheel turn together, a catch clicks onto the teeth of the ratchet wheel, preventing the cog from slipping backwards under the weight of the load. And the chain hoist is only getting started. With each transfer of force from gear to gear, the force from the hand chain gets concentrated more and more. The cog is also attached to the drive shaft. As the cog turns, it also turns the shaft. At the other end of the shaft is a small gear with 5 teeth. As that gear turns with the drive shaft, the force applied to the cog by the hand chain has already started to increase. So far, it's been multiplied by a ratio of 7 to 5, which means 1 force on 7 chain links goes to 5 teeth on the gear. The small gear is now turning with more force, which puts stress on the teeth of the gear. To decrease the stress there, that gear turns two identical gear wheels at the same time. That way, the stress of the gear's force is distributed across two teeth instead of one. So the small gear turns the 18 teeth on each of those identical gear wheels. These gears have a small 4-tooth axle on the other side, essentially another small gear, which will in turn multiply the force there by a ratio of 18:4. And that's not all. Those smallest gears turn yet another larger gear, which has 19 teeth. Those teeth concentrate all their force on the few links of the lift chain that fit into the last sprocket. Thanks to all those gears, the force from the hand chain has been concentrated again and again until it's been multiplied 30 times. The chain hoist, it's amazingly simple. With nothing more than a couple of chains and some gear wheels, it takes a small effort exerted over a long distance and concentrates it into a big force, able to lift heavy objects bit by bit. Now that is powerful. Next, on how does it work, the flexible rotary power tool. To transmit movement through a flexible cable, it has to be rigid and flexible at the same time. Its secret weapon, a helix. The flexible rotary power tool. It turns a burr to calf. With a heavy high-powered motor separated from the handpiece by a flexible cable, work can be done with ease. But there's a problem. The rotary movement of the motor must be transmitted to the tool through a flexible body. And a flexible body is a body that can be deformed. In order to properly transmit the rotary movement from the motor to the handpiece, this cable must not be deformed by that movement. So how can the rotary movement of the motor be transmitted through a flexible cable without twisting or deforming that cable? By the use of a helix-shaped structure. This kind of structure allows both flexibility and transmission of movement. But how does it work? The flexible rotary power tool, the control pedal, the motor, the flexible cable, the handpiece, and the burr. When the pedal is pressed, the electric motor begins to turn. It can reach 2,000 revolutions per minute. These revolutions are transmitted along the flexible cable to the handpiece, and the burr turns at the same speed. And what's found inside the cable allows the rotation of the motor to reach the handpiece. Surprisingly, the cable doesn't twist, it doesn't deform, and all the power of the motor is transmitted directly to the burr. To really understand how this is possible, let's take it apart. The secret of the flexible cable is an intricate assembly of steel wires. There's a primary central wire, around which are wound 5 steel wires. 5 other steel wires are wrapped around this first coil, but in the reverse direction. And 5 more wires, reversed, and finally 5 more again, in the reverse direction. Each of these wires is a helix-shaped structure. It's this structure that allows the cable to be flexible, meaning it can be deformed by bending without being deformed by rotation, which allows it to transmit the rotary movement of the motor without twisting. The helix structure responds rather uniquely to rotational movement. Instead of twisting itself, the structure actually contracts. And if the rotation goes in the opposite direction, the structure dilates. Now, if the cable was made of only one steel wire, it could not transmit fully and completely the rotary movement of the motor, because it would be deforming either by contracting or dilating. But by wrapping 5 wires one way over 5 wires the opposite way 4 times, each coil prevents its neighboring coil from contracting or dilating. So when one coil wants to dilate, its neighbor wants to contract, when the next is inclined to dilate, and so on. Simply put, this wire assembly is rigid while rotating. It cannot twist. So the rotation that happens at one end of the cable is transmitted in its entirety to the other end. Although each layer of wires prevents its neighbor from contracting or dilating, each wire individually can still move within the assembly, conserving its natural flexibility. Rigid during rotation while remaining flexible. Not bad. The flexible rotary power tool. Steel wires wound intricately to create a helix shape. It transmits the high-powered rotary movement of the motor through a flexible cable right to the burr. Powerful, efficient, and practical.